Good morning, students. In previous lecture, we have discussed about instantaneous power density, or we can say that was instantaneous Poynting vector. Now today we will try to find the time average Poynting vector, and to find the time average Poynting vector, let us start from the instantaneous Poynting vector. That was P instantaneous the cross product of instantaneous electric field component and instantaneous magnetic field component. And we know instantaneous E was minus alpha z cos omega t minus beta z. We have discussed this. The propagation is in z direction, positive z direction. The E component is along AX, and the magnetic field was e to the power minus alpha z. That is well known to us now because we have discussed these terms many times. So cos omega t minus beta z, and the lag with the angle theta eta. That is orthogonal in space, that is AY. Now the instantaneous Poynting vector we can find just by cross multiplication of these two, that is E naught e to the power minus alpha z cos omega t minus beta z in the direction of AX with cross product E naught by eta e to the power minus alpha z cos of omega t minus beta z with the angle theta eta AY. Now this is instantaneous Poynting vector, and if we have the instantaneous value and we want to find the average value, as our aim is now to find the average Poynting vector, and to find the average value we will integrate and find the average of it for one period. So to find average we can say now it will be PZT dt for the period 1 by t 0 t t. T is the period. To find this average value, let us simplify this from here. This is in the direction of AX and AY. From the cross product rule, it will give us AZ. So PZT will be E naught, it will be E naught square, e to the power minus alpha z, e to the power minus alpha z, it will be 2 alpha z. Okay. Now this cross product with this, that is omega t minus beta z multiplied with cos omega t minus beta z with angle delay angle. It will be in the direction of AX cross AY, that is AZ direction. Okay. These are this part and this part both are scalar, so the cross product will be just multiplication. Now if we will do 2 divided by 2. Then we can apply 2 cos A cos B formula and we can put it here. So that will be, we can say, E naught square by absolute magnitude of this e to the power minus 2 alpha z divided by 2. 2 cos A cos B means cos A plus B plus cos A minus B. So cos A plus B will be 2 omega t minus 2 beta z minus theta eta. This is cos A plus B plus cos A minus B. When cos A minus will be there, then this term will be cancelled out, this term will be cancelled out, and this will be plus cos theta eta. Okay, so these two, this is in equivalent form, will give this value. It will be in the direction of AZ. And if we will further simplify, then we can write this term, that is E naught square divided by 2 alpha z, this term with in the direction of minus 2 beta z minus theta in the direction of AZ, plus keep this with both of them, E naught square 2 e to the power minus 2 alpha z cos theta eta in the direction of AZ. This is instantaneous value. Okay, now we have to find the average value. For that purpose, we have to integrate this for a period 0 to t, pzt, from this equation I am talking about, dt, it will be average value. As now the important point is to find the time period. And for any sinusoidal signal, the time period is 2 pi by the coefficient of t, and the coefficient of t is 2 omega. So the period will be 2 pi by 2 omega. This is the time period of this, and this is free from t, so no need for that. Okay, this is constant. So for average value will be, apart from that, what we can say, this is cosine term for any omega t minus something, and the average value, that is this, for this term will be 0, because for any sine cosine term the average value of that for a particular period, for a fixed period, it will give you 0. So the average of this will be 0. The remaining term that is giving a average value will be this one. So P average for this portion will be 0, plus here 1 by t, 0 to t, E naught square divided by 2 intrinsic impedance e to the power minus 2 alpha z cos theta in the direction of AZ with dt. Okay, so if we will integrate and we will try to find, then this t for full time period, this t and this t will be cancelled out, the remaining term will be this. So average value will be E naught square divided by 2 impedance e to the power minus 2 alpha z cos theta in the direction of az. This is the time average pointing vector. Okay, so we can say this is the time average pointing vector, or we can say time average power density. Pointing vector, or this can be also termed as time average power density. It tells how much average power density is present. Now, time average power crossing a surface can be what we can write, time average power, this is power density. Now we want to find the power crossing any surface, can be written as, now average power can be written as, for surface integral dot ds, and for closed surface it can be written as p average z dot ds. Now this and this, these two are the average power crossing the surface. Now this is the average power density when it is traveling in z direction. Now consider wave is traveling in free space. Traveling in free space. Or we can say, if it is free space, then you can also say lossless dielectrics. Okay, if wave is traveling in free space or lossless dielectrics, in that case we will try to find the time average power density. So for that purpose we need to find the impedance, alpha, and this angle. These three things are required to know for that purpose. So first thing, that is intrinsic impedance, and we know the formula, that is mu by epsilon. We have derived this already. And if the medium is lossless, that is free space, then in that case we have alpha is equal to 0, and if alpha is equal to 0, cos 0 plus j sin 0. So we can say the theta will be equal to the 0. Now gamma is equal to alpha plus j beta. Alpha is equal to 0. So beta formula we know, that is omega mu epsilon. Okay. Now if we have these parameters, in that case the average power, either we can say time average power or time average power density or time average pointing vector, it can be equal to the E square by 2 divided by impedance magnitude e to the power 0, and cos 0 will be 1, and in the direction of AZ. So it can be written as E naught square by impedance in the direction of AZ. This is only for free space or lossless dielectrics, because these values are from there. Now let us consider the wave is traveling in lossy dielectrics. In that case, sigma will not be equal to 0, and alpha will be a real part of gamma, and beta will be imaginary part of gamma, and intrinsic impedance will be, I think, j omega mu, just match this, and here it is j sigma plus j omega epsilon. Yes, now match this impedance formula, and if we can find alpha, beta and intrinsic impedance from here, then we can put these values in the this equation to find the P average for that medium, for lossy dielectric medium. Okay, so the first one was when the wave was traveling in free space or lossless dielectric, then this will be the P average. Now when it is traveling in lossy dielectric, then it will give us the value by putting alpha, beta, sigma and impedance in this equation. Now the time average Poynting vector for good conductor, in that case sigma again not equal to 0, and for this condition sigma is greater than omega epsilon, and mu is equal to mu naught mu r, and epsilon is equal to epsilon naught epsilon r. These are the parameters for good conductor, and from the previous study we know for good conductor alpha and beta are equal, that is match this value. I think full was in square root, and intrinsic impedance was mu divided by epsilon divided by sigma. Match these values, and as alpha and beta both are equal, so theta will be equal to the 45 degree. Okay, now put these values, this value here, and find the P average. So it will be equal to the half E naught square divided by intrinsic impedance from there, e to the power minus 2 alpha z cos 45, it will give us root 2, 1 by root 2. Okay, it will be in the direction of AZ as it is already there. So if we know alpha, impedance, angle, then we can find the time average power density. Now let us solve some examples based on these concepts which we have discussed in last 2 lectures. Now let us solve one example based on Poynting vector and wave power. The example is the magnetic field component of the wave is given as this. The magnetic field component is in the direction of AZ. Now medium is non-magnetic. The first thing to find is the direction of wave propagation. The next is the dielectric constant and intrinsic impedance. the time domain expression of E, the time average power density, the net time average power crossing a rectangular plate of area this oriented along the YZ plane. We have to find these 5 things from this information, that is in non-magnetic material. So let us start from the basic equation of H of the plane wave. So we can write H naught e to the power minus alpha x cos omega t minus beta z. X comes from here in the direction of AZ. H component is in the direction of AZ. If wave is propagating in plus x direction, then there will be minus sign. If it is propagating, if it is plus here, then it means the wave is propagating in negative x direction. So from this we can say the wave is propagating in plus positive x direction. So just by seeing this we can find the propagation direction of the wave. Now next one is to find the dielectric constant and intrinsic impedance. So dielectric constant can be find out either we know intrinsic impedance or we know alpha and beta. So we don't know this. It is important. It is easy and important to know alpha and beta. If we relate this from this equation, then we can find alpha is 0. That's why here there is no term. So alpha is 0. If alpha is 0, it means the medium is lossless. It indicates lossless medium. Okay, and beta from here we can have 10.2, and omega is 6 pi into 10 to power 8. So we have information regarding alpha, beta and omega, and if we'll put the alpha here and we relate from this to this equation, then we can find H naught is equal to 0.2. We have these informations regarding that. And for non-magnetic material, the relative permittivity is relative permeability is 1. Okay. Now we know the wave speed can be written as, it is 1. Wave speed can be written as omega by beta. We have derived this formula, and that is for that can be further written as mu r epsilon r. Okay, and due to non-magnetic nature, this is 1, so it will be C by epsilon r. We know beta, we know omega, we know beta, we know C, we can find epsilon r from here. So put the value 6 pi into 10 to power 8 divided by beta is equal to 10.2, and put the value C of C here, 10 to power 8 under root epsilon r. Now you can find the epsilon r from here. That is the dielectric constant. Okay, relative value, it is unitless. Now the next is to find the intrinsic impedance under section 2. Intrinsic impedance, and we have the defined formula for that. If you can remember, then it was permeability by epsilon, and this can be written as mu naught epsilon naught times mu r epsilon r. So this value is well known term, that is 120 pi, that is discussed in last lecture, and the remaining term will be mu r by epsilon r. This is 1, so we can find it is 120 pi divided by epsilon r that we will get from here. So in this way it will give us intrinsic impedance. The value of epsilon r we can find 2.63 for the medium, and if we will put this value here, then we can find it will be intrinsic impedance, it will be equal to the, put the value of epsilon r 2.63 from here, then it will be 232.5 ohm. Okay, so in this way we can find the relative permittivity, or we can say dielectric constant, or and intrinsic impedance. Now let us try to find the time domain expression of E, and we know E is equal to E naught e to the power minus alpha x, as it is propagating in the x direction, and cos omega t minus beta x. It is in the direction of AE. We don't know now. Okay, and E naught can be written as we know E naught divided by epsilon naught, epsilon will be equal to H naught. So from here H naught times impedance will give us E naught. So from here we can find E naught is equal to the, if we will solve, it is known 232.5 and H naught is 0.2, so it will give us 4645. Okay, E naught will be this. Just I have multiplied this value from 0.2 E naught, and the remaining term will be cos omega t minus beta x in the direction of A. Now E, still we don't know AE. H is propagating in the z direction, wave is propagating in the x direction. We know AE cross AH is the direction of the wave. So we can say if it is in the direction of AZ and this is in the direction of AX, then what will be this? X, Y, Z. If we do cross product of AY and AZ, then we can get AX. So from there we can say AE will be in the direction of AY. That can be written here. AE should be AY. Now next part is to find the time average power density. That can be written as, we have derived this formula already, half square a to the power minus x cos theta in the direction of AX watt per meter square, average power density, or that is named time average Poynting vector. We know all the parameters, that is E naught from here 46.5 square divided by impedance, that is 232.5 times e to the power 0 cos 0, it should be 0 1, it will be in the direction of AX. The average power density will be, time average power density will be this, and if we will calculate, then it will give us almost it will give us 4.65 watt per meter square in the direction of AX. Now the last one, that is to find the time average power crossing a rectangular plate of area this. Now we have to find the power. So the time average power is equal to the power density times the surface that is crossed by the wave. Wave is propagating like that and it is crossing a surface which is having a dimension of 30 and 20 as it is given here. So when wave is crossing to this area, for that we have to find the total power, average power. So power density is given from here, 4.65 in the direction of AX, this is at the place of this, and dot ds. ds is, this is YZ plane, wave is propagating in the X direction, so ds will be dy times dy and dz as the plane, as the wave, as the crossing area is in the YZ plane. So ds can be written as 4.65 dot dy cross dz. It will give the third direction, that is in the direction of AX. Okay, so AX dot AX will give you unit and the remaining term will be 4.65 dy dz. This is nothing, just integration of dy from here to here, dz from here to here. So this is the area. It will give us 4.65 into area, that is 30 into 20 centimeter into 10 to power minus 4 meter. And if we will solve this, then it will give us 27.9 milliwatt as it is average power, okay, crossing a rectangular area. Now we can end at this point. Thank you very much.